So do you want to admit all now?
Yep.
Hello everyone, welcome. We'll wait for a minute while everybody joins. In the meantime, I'm launching a poll, so feel free to submit your responses if you wish. All right. All right. Hello everyone and welcome. Thank you for joining us today for our webinar Beyond Binding Fast Scalable Chaos Predictions powered by SILCS and AI. My name is Abhishek Kognole, and I'm Scientific and Business Development Manager here at SILCS Bio. We are joined by Dr. Wenbo Yu, Associate Research Professor at University of Maryland, Baltimore. And with us, we have Dr. Alexander Mackerel, Professor at University of Maryland, Baltimore, and co-founder and Chief Science Officer here at SILCS Bio. And also we have Stephen Cossert, who is Application Scientist at SILCS Bio. So if you know, at SILCS Bio, we work closely with Mackerel Lab as our academic counterpart, and together we are always pushing the boundaries of computational drug design. Today we are excited to share one more innovative application of SILCS technology, which is SILCS-Kinetics, that combines physics-based modeling and machine learning to predict ligand dissociation rates at scale. So before we begin, just a quick housekeeping note. Feel free to submit your questions through the Q&A section at any time during the presentation, and we'll try to address some of them directly, and we'll take others verbally at the end. Okay. And with that, let's get started. I will start sharing screen. Okay, if everybody can see this. All right, let's get started.
Hello everyone. Welcome to the webinar. Today we will be learning about how SILCS and AI can empower the scientists to predict the ligand unbinding rates in a fast and scalable way. Here is agenda for today. For those who are new to SILCS, we will briefly introduce the SILCS method. Then Dr. Wenbo Yu will present the SILCS-Kinetics module, followed by validations and feedback. We will then take you through some quick updates regarding SILCS Bio software releases. And lastly, we will end the webinar with a Q&A session. Let's begin with an introduction to SILCS. The fundamental idea behind SILCS, which stands for Site Identification by Ligand Competitive Saturation, is to use simple chemical solutes to map the functional group affinity of the entire protein. The probe molecules, along with water molecules, compete with each other to occupy the most favorable interaction sites on the protein surface. We extract this information, analyze, and process it to generate a pre-computed ensemble of affinity maps, which we call frag maps. We will show how this one pre-computed ensemble can then be used for various tasks in drug design campaign, such as site identification, virtual screening, hit identification, hit to lead, and lead optimization. Here is what undergoes in a silk simulation. We start with a protein and immerse it in a box with SILCS probes. Note that there is no ligand present in this case. 10 systems of the solvated target protein with scrambled side chains are generated as starting structures for 10 independent runs. We then run each of the 10 systems for 100 nanoseconds of MD simulation. After 1 nanosecond of MD simulation, we introduce an enhanced Grand Canonical Monte Carlo, that is GCMC simulation, for 100K steps before resuming the rest next MD simulation. Here, the MD simulations allow for conformational sampling of the protein as well as the probes and waters. And the GCMC simulation allows for sampling of probes in the deep pockets. The information from this huge calculation is then processed to generate the frag maps as shown on the right hand side here. To do that, we divide the full 3D space into tiny cubic voxels and calculate the probability of each probe occupying the voxel. Now here is a representation of what we find in the presence of a protein. The probability of the probe molecule occupying a given voxel is driven by its favorable and unfavorable interactions with the protein. There are regions with higher and lower probabilities than the probability of probes interacting with each other in the absence of the protein. And importantly, there are regions with no probability. All these probabilities are then normalized with the bulk solution probabilities and Boltzmann transformed to get a grid free energy at each cubic voxel. This is done for all types of atoms in the set of probe molecules, giving us the final frag maps. Now, we can visualize these frag maps in reference to our starting structure, visualizing different frag maps that represent apolar, hydrogen bond donor, hydrogen bond acceptor, positively and negatively charged regions can be quickly analyzed for qualitative assessment of your target. Additionally, different GFE levels allow for regions that will bind the specific chemical class most tightly to be identified. Unfavorable regions may also be identified. Now, to use frag maps in a quantitative way, we first take the ligand pose and overlay in the field of frag maps. We then take each ligand atom and assign a frag map type to it. Then, based on the location of the atom and the grid free energy at that location, we can then get an atomic contribution to the ligand's energetic favorability. Basically, we can get an atom based free energy contribution that can be summed into a score that we call LGFE, ligand grid free energy. This LGFE score is an estimate of binding free energy of the ligand in that pose. Because the frag maps are pre-computed, this simple assignment and summation is instantaneous and becomes the core of this technology as we move forward. The SILCS technology is not limited to overlaying ligands onto frag maps. We can also subject the ligand to the conformational sampling using what we call SILCS Monte Carlo or SILCS MC docking. In MC docking, we sample the translational, rotational, and torsional degrees of freedom of the ligand in the field of frag maps. The Metropolis criteria uses intramolecular energy of the ligand conformation and the LGFE to optimize the function of finding the best ligand pose and most favorable LGFE score. We can do this in a full docking mode where we are sampling the full rotational and translational space of the ligand in, say, a binding pocket, or in a mode we call pose refinement, which is more local relaxation from a known starting conformation, such as from a core crystal structure. The full docking takes typically an order of approximately 1 minute or so, so representing a speed up of over 1,000-fold compared to traditional free energy calculations. Here are results from a recent validation study that compares the free energy perturbation methodology with SELCS method. We have presented a comprehensive study of approximately 200 ligands across 8 different targets, where we compared silks with number of previously published FEP studies. It is very evident that LGFE scores provide highly comparable relative binding affinity to the free energy perturbation calculated delta G values. And when using iteratively with experimental data, and this experimental data can be for small number of compounds as small as 10 molecules, we were able to improve the relative ranking of the ligand affinities shown by the percent correct data here on the right column, where for standard silks the percent correct was 0.71. With silks MC machine learning optimized approach, we can get it up to 0.81, which is on par and above the standard free energy perturbation methods that are out there. To summarize the key advantages of Silk's bio approach, it is the pre-computed GFE frag maps, allowing rapid and accurate ligand binding affinity estimates in a way that leads drug design process. And beyond the quantitative predictions, usually the frag maps easily allow for an understanding of types of functional groups that can be added to a molecule to increase its binding affinity, which is very useful in the medicinal chemistry to give ideas about synthetically accessible molecules. We note that frag maps explicitly count for protein flexibility. This is important because we know the protein can undergo local conformational changes in presence of different ligands. The frag maps account for desolvation effects, and this refers to the normalization procedure which we described earlier. In addition to globular proteins, we also support membrane proteins such as GPCRs, ion channels, and transporters. We also have a specifically optimized protocol to apply the same method to RNA targets.
And now I will hand over this presentation to Dr. Wenbo Yu.
Thank you, Dr. Cogno, for introducing the SILCS method. Now we will introduce the ligand and binding kinetics application of SILCS. When we talk about drug binding to a target, there are multiple dimensions to describe such process. The generally used binding affinity, which is linked to the KD measurement, is calculated using two kinetic metrics K on and K off, and represent for the free energy difference between bound and unbound states. While K on and K off is related to the energy barrier between the two states and are linked to the ligand residence time. So drug efficacy had been shown to correlate better with drug binding and binding kinetics than binding affinity alone in selected systems. An illustrative example is a study conducted by researchers from the Leiden University and the Vertex Pharmaceuticals Company. And they are targeting this chemokine receptor 2 CCR2 protein. For this protein, there were high affinity inhibitors which were shown to lack of efficacy in the following clinical trials. And in this study, through integrating structure kinetic relationship along with the traditional structure activity relationship analysis, they were able to design a high affinity CCR2 antagonist with a very long residence time as shown here on the bottom, in contrast to an antagonist with a very short residence time, but also with high binding affinity. So this study illustrated the benefit to have kinetics consideration in the early stage drug development. Since kinetics is important, similar to binding affinity prediction, computational methods are again valuable tools for efficiently design high potential binders with good kinetics profile. Molecular dynamics again can be applied for this purpose. Since ligand unbinding often occurs on microsecond or longer time scales that generally exceed conventional MD capabilities, a range of refined MD-based methods are available on the market, including enhanced sampling MD method, path sampling weighted ensemble, and Mach state modeling method. Beyond, surrogate modeling with machine learning has also emerged, where molecular mechanics derived descriptors are used to predict kinetic rates, typically for individual protein targets, and is usually focusing on the bound state in the active site and ignoring the full unbinding event. For the IMD-based methods, two key requirements for computational kinetics studies are identification of the unbinding pathway or relevant collective variables and the calculation of the free energy profile along the pathway. Since SILCS can evaluate ligand binding free energies while mapping the full protein free energy landscape, including regions beyond the binding site, thus in principle the rich information from SILCS can also be used to characterize ligand and binding profiles. Here we describe how SILCS can be applied to predict unbinding pathways and compute corresponding free energy profiles, and eventually how this physics-based model can be integrated with AI to enable a scalable SKR computational IC. The first step is pathway determination using SILCS. Traditional pathway identification methods such as CAVR rely on geometric or topological analysis in which protein structures are discretized into 3 degrees and protein atoms are treated as obstacles. Then shortest path algorithms such as Dijkstra's algorithm can be used to identify routes from the binding site into the box solvent. These approaches are typically based on static structures and limited ensembles of structures and focus primarily on geometric accessibility without considering binding energetics along the path. In contrast, as the example shown here for protein HERG, our SILCS frag maps are 3 degrees in which voxels encode both solvent accessibilities via exclusion maps that naturally define obstacles with implicit flexibility consideration. Also, those voxels encode fragment-based free energy information represented by SILCS frag maps. So this enables the shortest path algorithm to identify unbinding pathways guided not only by geometry but also by energetics. Because SILCS inherently accounts for protein flexibility, SILCS-based pathway determination method can offer a more physically realistic alternative to the traditional rigid structure method. To use SILCS frag maps for path finding, we need to choose an optimal path finding algorithm. We take a look at the two popular path finding algorithms, including the exhaustive Dijkstra path finding algorithm as well as its attention A-star algorithm. The A-star algorithm speeds up the path finding process by introducing a heuristic function to guide the search for a given weighted graph. So A-star would be a faster and smarter algorithm to find pathways in our application scenario. In the A-star algorithm, path finding is guided by minimizing a cost function f composed of two terms, g, the accumulated cost of the current path, and h, a heuristic estimate of the remaining cost to target. So here Hn is defined as the Euclidean distance from node n to the target, and in conventional A-star, G reflects obstacles in the search space. In our case, as illustrated on the right figure, 1 represents for the forbidden regions in our exclusion map, and these values are served as the obstacles to get the calculation of G. And as a note, 1 is only for illustration purpose, and in practice we use 1,000 as the number for solvent forbidden regions. To incorporate binding preferences, we augment the cost function with SILCS GFE frag maps. So free energy contributions from multiple fragment types such as apolar, hydrogen bonding donor and acceptors, as well as positively and negatively charged fragments, as illustrated in this figure, are summed and further combined with the exclusion map. And the resulting cost landscape, as shown by brown colored grid, can guide A star to identify pathways that both avoid steric barriers and favor energetically favorable regions. So in practice, we also add a weighting factor in our cost function in order to balance G and H and to enable the algorithm to efficiently identify unbinding pathways that exit the protein while favorably sample the favorable interaction sites along the path. This example illustrates the advantage of incorporating both SILCS exclusion and GFE frag maps into the A star cost function. So first, the top left panel shows the DHA protein case with its solvent accessible surveys rendered from the crystal structure used for SILCS simulations. The 5 known unbinding pathways are indicated by yellow arrows from the binding site as shown by the sun icon. And it's noticeable that P3 pathway is inaccessible in this static crystal structure. Panel B shows the SILCS exclusion map for DHA protein, which incorporates protein flexibility and thus enable identification of this P3 pathway. Thus, pathways missed in the rigid structure analysis become accessible when SILCS-derived flexibility is included. And on the right, we show another example where the A star pathway is computed using only the exclusion map as shown in blue versus the exclusion map combined with GFE frag maps shown in red. So the blue pathway follows the shortest geometric route to the tunnel exit. The red pathway, though, is guided toward energetically favorable regions as shown by the yellow dashed circles, even at the expense of path length. As highlighted, the GFE guided path sampled apolar and hydrogen bonding acceptor hotspots that are bypassed by the geometry only path. So this demonstrates that including GFE information can yield a pathway that better reflect ligand-protein interaction preferences along the unbinding process. So now we have this algorithm, and the A star algorithm requires both starting and ending point. Starting point will be set by the user as the binding site coordinate, while ending point should be a coordinate in the bulk around the target protein. In order to define all possible unbound states of a ligand, we use Fibonacci lattice mapped onto a sphere that covers the target protein. And these Fibonacci lattice points will serve as evenly distributed ending points for our A star algorithm. As shown on the right, the mapped Fibonacci lattice points nicely cover the protein, and thus by running A star pathfinding between the user-defined starting point with every lattice point in the bulk, we were able to get possible dissociation pathways toward different directions. User has the freedom to control the resolution, and in our practice, 500 points are enough to well sample a regular-sized protein system. To make sure we cover the full protein surface, some of these Fibonacci points are actually far away from the protein surface, so that the calculated pathway is way into the solvent, as illustrated by the middle figure. And this can cause issues in the later stage. One obvious drawback to have such long paths into the solvent is more calculations will be wasted on these extra bulk coordinates. Another fact is that there will be some pathways that share exactly the same path in the protein, while only differs after entering the solvent, since they are targeting different ending coordinates in the bulk. To facilitate with the following pathway analysis, we need to truncate such pathway to keep only the essential portion for the energy profile calculation. Thus, we assign a sphere to keep each lattice point with a radius based on the nearest protein atom, and any pathway coordinate that encounters one of those spheres will be terminated and only keep the essential portion left as illustrated by the green lines in this figure. Because many putative pathways are generated, multiple pathways often sample the same dissociation channel. For clarity and efficiency, similar pathways are clustered so that each cluster represents a unique unbinding channel. Pathway clustering is non-trivial because pathways differ in length, making simple geometric distance metrics unreliable. To address this, we adopt the dynamic time warping (DTW) technique from the signal processing area, which provides an optimal alignment between two sequences that are not fully synchronized. So as illustrated on the right figure, in panel A, there are three pathways connect the binding site to the bulk solvent through two channels. And visually, the red and blue pathways belongs to the same channel, while the green pathway is distinct. So as shown on panel B of this figure, direct pairwise distance calculations incorrectly suggest that the red pathway is closer to the green than to the blue, as reflected by these numbers. However, DTW aligns corresponding segments of unequal length pathways, yielding a small DTW distance between the red and the blue pathway, which has a DTW distance of near 9, than between the red and green pathways, which has a DTW distance of 10. So thus, DTW provides us a meaningful similarity metric for robust pathway clustering in our workflow. We then apply our SILCS-based pathway identification method to the DHA protein, and previous MD studies identified 5 dissociation pathways labeled as P1, P2A, P2B, P2C, and P3 for wild type and mutants. Using our approach as shown in panel A, 4 of the 5 pathways were captured. The missing pathway, which is P2C, emerged only when the A star cost function was restricted to the exclusion map as shown in panel B. So this indicates that drug-like molecules prefer the other 4 pathways over P2C. And this is consistent with the previous works that P2C primarily serves as the water exchange pathway and is rarely utilized. So these results suggest that exclusion map only search are suitable for small species such as water and ion, while the other one can capture dissociation pathways for drug-like molecules. We also validate our method using 6 additional proteins as listed in this table. And as shown on the right as an example, the 4 kinases, including P3 map kinase, ABL, SRC, and c-KIT kinase. So previous enhanced sampling MD studies has summarized the possible unbinding pathways, including the G-rich, A-loop, hinge, and hinge orthogonal pathways. So our method was able to find all these pathways, though different preferences are seen for different kinase proteins. And this serves as a further validation of our method. To compute free energy profiles along unbinding pathways using SILCS-MC, cylinder shapes or slabs are used instead of sphere shape, which was used for standard SILCS-MC. Because slabs provide better control along the pathway direction to define a channel, while their radius is adjusted based on the channel width defined by all pathways in a cluster. For each slab, SILCS-MC docking can then be performed, and the best scoring pose is retained to represent the local bound state. As shown in panel A, the DTW pairings are first used to generate the mean pathway coordinates, shown in panel B in red. And then for each coordinate I, the slab orientation is defined using the previous I-1, the current I, and the subsequent I+1 points to obtain a smooth local path direction. Slab radius are then determined to cover all paired coordinates from pathways within the cluster. Cylinder shape or slabs are then constructed along the mean pathway used for SILCS-MC docking and can yield dissociation free energy profiles. So using the neighboring points to define slab orientation avoid slab overlap in highly curved or zigzag pathways as illustrated on the right. So defining slab planes perpendicular to the locally averaged path vector produce smoothly stacked slabs with minimum overlap, enable robust sampling along the bending channel. And in panel F and G are some examples of the slabs being generated for two proteins. Now we have the two key components defined for SILCS in order to model kinetics, including pathway determination and free energy profile calculation. We are ready to test it. As a first validation, dissociation of benzimidine from trypsin, which is the commonly used system to study kinetics computationally, was explored. So multiple dissociation pathway clusters were identified for trypsin using our protocol, and the three most populated pathway clusters are shown on the left by different colors. So their final binding states before entering the bulk phase are also shown. So, and we compared our result to a study using enhanced sampling MD method from a previous work, as shown on the right. The predicted binding pose of benzimidine at the active site is shown in the orange dashed circle. The previous work identified three metastable states is labeled as S1 to S3, and S4 is actually the bound state of benzimidine. And you can see that the three metastable states are very similar to the three metastable states captured by our protocol. And the LGFE values for these three states and the active site binding are in the same order with the reported relative free energies of these three states from the previous work, even though the quantity differs a bit. So also we can measure the energy barrier for each pathway, and the state S3 was evaluated to have the lowest energy barrier, which is consistent with the previously constructed PMF surface as shown on the right corner, which suggests transition between bending state S4 and metastable state S3 has the lowest energy barrier. Beyond the barrier evaluation, there are more information could be analyzed. The bending poses along the pathway can be checked. So for this example, the pathway leading to metastable state S3 can be analyzed. There are several important bending states along the pathway. For example, shown on the far left at the active site, the bending pose reproduces the crystal bending orientation of benzimidine. The protonated amidine group forms a salt bridge interaction with the active site residue D189, and this interaction is captured by the SILCS positively charged MAMN frag maps. The importance of this contribution is indicated by the very favorable GFE value of negative 2.9 kcal/mol of the amidine group. Another binding pose along the pathway captures a state when the molecule first exits the active site with the amidine group tilted outward, As indicated by the frag maps, the emitting group still makes a favorable energetic contribution through forming an hydrogen bonding interaction with the backbone carbonyl group of the glycine 212. And however, the GFE value of the emitting group becomes less favorable than in the active site. It goes down from the negative 2.9 to the negative 1.8 kcal/mol, which is the dominant contribution to the energy barrier we found in this energy profile. And actually, this state is very similar to the meta-stable state identified in a previous work using meta-dynamics enhanced sampling MD method. So all the binding poses along the pathway could be further analyzed and may provide item-wise information for structural kinetics relationship development. We then further tested our method using more proteins. This includes 8 proteins done initially for our further validation and used as training set to develop a machine learning model. And we also tested 5 extra protein systems in order to further independently validate our physical model and AI model. These proteins covers a broader range of protein types and sizes, which has experimental K-off values available. To estimate energy barriers related to ligand residence time, we evaluate multiple energy terms derived from SILCS-MC. In a conventional model, ligand unbinding is described by a single barrier model and can be further extended into a two-barrier model as shown on the top left, where the ligand is first translocated over the initial barrier from the binding site to a surface metastable state, and then cross an additional barrier to enter bulk solution for hydration penalty. So multiple barriers model in which the ligand first across barriers connecting the binding site to intermediate mate-stable states and the surface mate-stable state, followed by a final barrier to enter the bulk solution, as shown on the right, is most suitable to describe the energy profile we generated. Because SILC's GFE are normalized to bulk solvent, the free energy of a ligand in bulk is zero. Thus, the final dissociation cost from the surface metastable state to bulk is 0 minus LGFE of the surface metastable state. So along the path slabs, the SILCS-MC provides LGFE profiles that capture local minima and barriers associated with the intermediate states. In addition to the ligand-grade free energy, intramolecular energy, IE, was also included to account for conformational strain, which can be significant when ligands traverse narrow bottlenecks in the dissociation channel. So thus, here we evaluated 4 energy barrier models for correlation with experimental K-off values, including LGFE, the LGFE of the surface metastable states, as well as the intramolecular energy, IE. In addition, we also tested 3 ways to consider pathway clusters, including using only the largest pathway cluster, using the cluster which gives the lowest energy barrier, or using all clusters and calculate an average energy barrier. Combine this with different energy barrier evaluation strategies, we tested 12 ways to calculate energy barrier and tested them using 8 proteins. The Pearson R for correlation between calculated energy barrier and experimental K-off are shown in this bottom figure. Though different performances are seen for different strategies, the E4 plus P2 strategy gave us the most consistent result across all protein systems, and thus will be further considered. Shown on this slide is the correlation plots for all 8 tested proteins using this E4 plus P2 strategy. So satisfactory correlations are observed, especially for protein systems where we have a lot of experimental K-off values available. To enable high throughput establishment of SKR, we further developed models that directly predict K-off rather than the intermediate energy barriers. Given the strong correlation between SILCS-derived energy barriers and experimental off rates, as we show on previous slides, SILCS energy terms were used as input features for machine learning model training. So two model classes were evaluated, including a decision tree-based regressor, which can use scalar energy barrier features as input, as well as a recurrent neural network architecture, where leverages full energy profile as sequence-based input, allowing the model to learn pathway-dependent features beyond a predefined single scalar barrier. So the dataset comprises 235 data points across 8 proteins and split into training and test sets using the stratified sampling in order to preserve the experimental K-off distribution as shown on this right figure. So in addition to the energy terms, molecular size descriptors such as molecular weight and rotatable bonds were included in order to account for diffusive contributions to the unbending kinetics. For machine learning models using pre-calculated energy barrier, we tested four tree-based machine learning architectures, including the random forest, the GB, XGB, as well as the LGBM methods. We used a reasonable range of different hyperparameters for model tuning, and the final adopted values are shown in bold fonts. The performance of the four models are shown in the right table, and the random forest model performs slightly better than others, considering both the RMSE and the Pearson correlation R. So in the input feature importances for the random forest model are shown on the right bottom corner. And you can see that the molecular weight has the largest contribution, indicating the importance of including a diffusion-related term in the model. Energy barriers features as well as the number of rotatable bonds have similar importance values, indicating their contributions to the model as well. So here we also analyzed the correlation between molecular weights and the experimental K-off values for all the data points. We observed a very weak correlation, which indicates using the molecular weights alone cannot determine the K-off value precisely. So which further validates the importance of including other input features in our machine learning model. This slide shows the correlation plots on the training and test set for the random forest machine learning model. The performance drop for the test set compared to the training set indicates some level of overfitting, even though the hyperparameters were constrained to reasonable values during our training. So such overfitting issue is well known for tree-based machine learning models. Next, we explored using the full energy profile on the bending pathway for machine learning model training. Because LGFE and IE profiles are variable lengths and poorly aligned, they cannot be used directly as scalar features. We therefore use a long short-term memory-based recurrent neural network to encode each profile into a fixed representation, which can then be combined with other scalar descriptors via a multiple layer perception to predict the K-off values. So the RNN model was originally designed to take a variable length time series data as input, to memorize important information from each time point and condense the information in order to learn from the time series as a whole, and this satisfies our current need. We also tested a range of hyperparameters to tune the model as listed in this top right table. And the performance of this model are shown in the bottom right table. And you can see the performance across different sites very consistent. Again, the correlation plots on the training and the test set for this RNN plus MLP model are shown on this slide. And it can be seen that the performance of such machine learning architecture on the training set is slightly worse than the random forest. However, the performance on the training set and the test set is much more consistent than random forest, indicating that the overfitting issue is well controlled at here. Beyond the test set, we further validate our machine learning models using 5 independent protein systems. This slide shows the random forest model performance. Satisfactory correlations are seen, especially for the protein systems that have more data points. This slide summarizes the performance of the RNN plus MLP model. Compared with the random forest model, the RNN plus MLP approach shows superior performance for the proteins with most data points, including RIP1, FAC, and SEH, based on both RMSE and Pearson correlation metrics, indicating its greater robustness. Both models tend to overestimate the negative log k-off values below around 2 and underestimate values above 2, a trend also observed in previous machine learning model studies of unbinding kinetics. This is likely due to the sparse training data on the two extremes. But overall, both models exhibit reasonable predictive accuracy and are suitable as dissociation rate predictors. As a short summary, we have a fully automated workflow for SILCS-Kinetics. It is fully automated and only requires a limited number of inputs from the user, including the protein structure, the binding site position, and the clustering cutoff, as well as the ligands. It has a set of components starts from the Fibonacci point generation, a star algorithm-based pathway finding, and following pathway clustering to generate SILCS-MC simulation slabs. And then after SILCS-MC, energy profiles can be extracted and used to predict k-off directly, or used to analyze all binding states along each pathway in order to establish a full structure kinetics relationship. Through this workflow, multiple intermediate files will be provided for the user in order to visualize and analyze the results. Also, the user has their own freedom to retrain the machine learning model by using the experimental k-off values. At the end, we want to highlight the following features of our SILCS-Kinetics workflow. By integrating SILCS exclusion maps with energy grids, this approach identifies ligand dissociation pathways that account for both protein flexibility and functional group binding preferences. It predicts metastable states along the pathway and enables detailed analysis, including atom-wise energetic contributions. Combined with machine learning, this SILCS-based physics framework provides a fast, scalable computational IC for predicting k-off value and establishing structural kinetics relationships in early stage drug discovery. Thank you everyone for your attention.
Thanks, Wenbo, for that detailed presentation of SILCS-Kinetics workflow. Dr. Wenbo Yu is our academic partner in taking the SILCS technology to the next level. At SILCS Bio, we are making these workflows available to our academic and industry users by further improving the accessibility and applicability to broader systems of interest. So today we are excited to include SILCS-Kinetics in our upcoming release of SILCS Bio software suites as an add-on module
to either of the small molecule or covalent or biologic suite. This allows the users to opt for the module if needed. The new 2026 release for the software suites is in works, and we hope to get that out soon. We are actively looking for beta testers at this point, so if you're interested, please make sure to contact us. Thank you again for tuning in. For more details on our new developments, please visit docs.silksbio.com. And for general inquiries, please visit us at silksbio.com or email us at info@silksbio.com. We are happy to take any questions now.
Right. Can ask questions in the Q&A section if you need it. Right. We have, yeah, some people have started asking questions there. Does it work for peptide protein interactions? Dana asks. And the answer is yes. You can use a peptide molecule as a ligand for SILCS-MC docking. However, yes, if you have really long peptide, you'll need to adjust the parameters that are used in the docking calculations. His next question is there a plan to implement a post-processing script to measure or account for competitive pathways for co-reactants similar to the occupancy calculations for SILCS biologics? Alex, you want to reiterate your answer?
Sure. This is the workflow is post processing.
Yeah.
This could certainly be done. Again, because you can do multiple pathways, multiple ligands, and we do have the ability to do two ligands simultaneously. This is certainly possible. If users are interested in that, we would be able to work with them to get it set up and running.
All right. And then next question is, can you describe a workflow in which you would use if you wanted to measure and compare on off kinetics of a ligand with non-specific binding that competes with the active binding sites?
You'd have to, yes, you'd have to have some idea of where these alternate sites are. You would then go in for each alternate site. You would reproduce the pathway determination, and then you could include the additional pathways into the SILCS-Kinetics calculation, and then you'll have all the different pathways from the different individual sites and take them into account.
Okay. And then, is there going to be an academic license or trial option, and how would I go about obtaining it? Yes. So we already have licensing for academics. Typically, for academics, we just do the whole site license, meaning that you'll get the uh, bundle of all the suites together, in one go. And you can obviously get a 2-month trial license for that as well. Just reach out to us at info@silksbio.com and we can give you more information on that. Next question from Silas. Will the experimental data that was used to build the ML model going to be made available with the software distribution for use in training new models by users? Wenbo, you want to?
Yes, so we already published all those experimental K-off values with our publication, but also like we have an electronic version, so that can be distributed with the SilksBio suite. So then to allow user to bring in more experimental K-off values to retrain the machine learning model. Yes.
Okay. Then we have a question from Tikshana. Can we do this with multiple proteins involved in a pathway and see the signaling impact with multiple ligands? Interesting question. Alex, you want to take that?
Well, the method, it's beautifully scalable, right? So if you have you once you set up one protein, you do the pathway calculation, you do and you're ready to do the kinetics, and you've got the maps all done, it's ready. Okay, then you can add a second protein and then add a third protein. And as you add each new protein, you have to do the initial silk simulations, which takes some time. But once that protein's there, it's all ready to go. And given that the each ligand takes a matter of, say, minutes for the SILCS-Kinetics calculation, you can quickly add in as many proteins as you'd like and just build up. So it's very scalable. Yeah, we're looking into doing very similar types of studies, including working with transporters and so on. So there's a lot of interesting places that this technology can be taken.
All right, thanks. Kazi asks what edge it provides over the other docking softwares like Autodock or Schrodinger. Uh, Wenbo, you want to take that?
Yeah, so like Autodoc, like definitely they are more focusing on the binding site itself. But again, like you can also provide some coordinates along a pathway you determined using other kind of softwares and start a docking. But our method is more integrated and offer you a way like to do this pathway analysis plus the docking along the pathway. Alex, do you want to add something else?
Yeah, I just say that the Silks technology in general is because you're doing a free energy calculation that takes into account protein flexibility. So even just docking individual ligands, you're getting free energy information in a rapid fashion that includes information on the contribution of individual moieties, atoms in the molecule to the free energies. And when you extrapolate that to the SILCS-Kinetics, as you go along a dissociation profile, you can understand what parts of the molecule are contributing to the barrier, which gives you the information for rational optimization to say maximize interactions at the barrier to slow down the off rate if desired, or to just improve the binding affinity and so on. And again, because it's so scalable, the technology is very fast and efficient.
All right, thanks. Yes. Naz asks, is it applicable with intrinsically disordered proteins? Uh,
Well,
yeah, good.
I mean, for any docking, you need a structure. Okay, at some point, now if
Yeah,
you have an intrinsic distorted protein and you can generate maybe a collection of a few ensembles of structures, you could apply the methodology, but it's a structure based approach, so you need some structure. So unto itself, it's hard. But alternatively, if you have a protein that your intrinsically distorted peptide binds to, the Silks method is very efficient for doing, you know, peptide protein docking, even protein protein interactions, and so on. So there's a lot of space in that context, and so on.
yeah. All right. One more question along the previous question. How does this method compare to enhanced sampling MD in terms of accuracy and costs? Yeah, I think when Bogan take this, right? You mentioned all these methods in the start. Uh,
Yeah, so in the slides, like we went over some comparisons like between our method versus the enhanced sampling MD method. So seems our method, at least for the test system we are using, can capture important metastable states along the pathway. But yeah, so enhanced sampling MD is more mechanistically like rigorous, but it's very computational expensive and empirical for hundreds of ligands, right? Like, so, but SILCS-Kinetics sacrifice some dynamical details for throughput, so then it making it more useful in the early stage screening. Alex, do you want to add something? Yeah.
Yeah, well, I mean, for each ligand, calculating the pathways is like 1,000-fold, 10,000-fold faster. And with enhanced sampling MD, they've never been able to do a collection of ligands like we presented today. It's just way too slow. So in some ways, it's impossible to do a comparison because enhanced sampling MD methods cannot be applied to tens of ligands, let alone hundreds of ligands that we've looked at. So, the methods just can't even go where SILCS-Kinetics can go. SILCS-Kinetics is offers a whole area of opportunity that's just not out there in the field.
Yeah, the core method of like focusing on protein first and then, evaluating ligands quickly afterwards makes that difference versus in enhanced sampling, you would have to run all these calculations again and again for. So, okay, next one. What are computational requirements for the tool? Yeah, we have this mentioned on our documentation website at docs.silksbio.com. Basically, you will need, for that upfront calculation of silks simulation, you need to have a GPU cluster, which helps to get the frag maps faster. But you can have a few GPU available, and then you can, get to the frag maps maybe in a day or two. But then running the frag map the SILCS-MC docking calculations is really, really fast. So overall, you will need uh, uh, at least at the minimum a workstation, a Linux workstation with a GPU uh, enabled environment. Okay, then we have how much will the cost be? Yeah, you can reach out to us at info@silksbio.com and we can provide that information for you. The next one is Tanisha. Can we use this when two different protein is involved in the same pathway? I think Alex kind of explained that a little bit in the previous question that if you have more proteins, you'd have to run them separately and then evaluate the results together afterwards, right? Okay. One more question I think we can take. How reliable are the K-off predictions compared to experimental measurements across different target classes? Wimbo, you want to take that?
Yeah, so the model like shows reasonable correlation on the benchmark data set as we show through our talk, right? But the performance is also varies like by protein family. So that's why we use the external file independent protein systems to test if the machine learning model can be generalized, and the result is actually pretty satisfactory. The performance like difference between different proteins reflects both difference in the binding site flexibility and the data quality we use. But I would say like it's not going to fully replace the experimental kinetics assay, right? But it's similar to docking. The approach is better seen as a ranking tool, like in virtual screening, to come up with a list of candidates with high potential, with good, kinetics profile. Alex, do you want to add something?
No, that addresses the question
All right.
quite well.
Perfect. I think we are out of time and a little bit over. So yeah, thanks everyone again for joining in today. We will be putting a recording of this as well soon uh, on our website as well as our LinkedIn page. So feel free to share it with anyone who might be interested after this. And yeah, do reach out to us if you are interested in beta testing. We are happy to accommodate that. And
Abhishek, just do we
yes.
have a YouTube? We have a
Oh,
YouTube.
yes, yeah. So the video will be on a YouTube channel, but then it will be linked on our website and everything. So, but yes, do check out like our previous webinars, which are over there. We recently released covalent suit. Then we have a silks water and previous release webinars over there that you can go and check. So yeah, thank you very much again. Have a good day. Bye.
Thank you.